Hello there. Another fantastic YouTube video from Mr. Keller. So here's the deal. I'm going to use the shell method to do something that's a little bit more akin to the disc and washer ones that you had, number 7 and 8, where you had to rotate a half circle around to get a sphere. And I think number 8 was something about finding a solid and then drilling a hole down through it. So those were disc and washer methods. I figured this would be a good way to do the shell method, but we'll actually use it to prove a volume formula for the right circular cone. So we'll show you how that works. I'm going to figure out what a right circular cone looks like. I think everybody probably knows, but the idea is that we're forming this. Okay? So the altitude or the height perpendicular to the radius, hence the right part of this, R-I-G-H-T. And then circular, obviously circular base, and then cone because it's a cone. So that's kind of the shape we're after. I'm going to do it a little bit differently. Let me get rid of this little mini guy here. No, maybe not. Let's put it okay. So I don't know. I'm just going to draw me a triangle, a right triangle on these axes. So there's my y-axis, there's my x-axis, and then it's going to be kind of cool. Now, you know the formula for a right circular cone because that is a basic geometry formula from 9th, 10th grade, 9th for you guys. So here's the deal. We have a right triangle. Let's see. We're going to have to rotate this around the y-axis the way I drew it. And if I'm rotating around the y-axis, the key point to the shell method was trying to figure out what your slice looks like. That's always the problem. And then the idea is that we're using the shell method if our slice is parallel to the axis of rotation. Well, my axis of rotation is the y-axis, so parallel would mean a vertical slice. So I'm going to draw in my vertical slice as such. And then what we're going to think about is rotating this around the y-axis. And we're basically forming a cylindrical shell. All right. And I'll try to draw this. Well, it's kind of hard, but it's basically like for fitting times, it's a roll of toilet paper. And then that'll change. If I move this cylindrical slice over there, what we're going to do is we're going to wrap that thing around it, and we're just going to get another roll of toilet paper. So that's kind of the idea of what's happening. Now, these, I like to think of them almost as like Russian nesting dolls because they're all nested inside of each other. And I mean, my hands are forming kind of like concentric cylinders, but they're shells because the cylinder itself is not filled in. Okay? It's kind of like, well, the giant piece of weird art that I have in my room that is a perfect example of a cylindrical shell. Now, if we could just mass produce like slightly smaller ones and slightly bigger ones, we could stack them inside of each other, and then we could add up all of those shells, and we'd have the volume of whatever region we wanted. So that's kind of what we're doing right now. In case you don't remember the thing in our classroom, it is the piece of art that was painted by a student. Basically, it's just like a big old giant toilet paper roll, except it's really big and really heavy. And I think Lanning stuck himself inside of it and started to roll. And I know Cole did that last year. So anyway, that's what we're thinking about. And if we're going to rotate, so the key piece, back to the math, is we need to get our radius down. And the radius, like anything, is from the axis of rotation to the slice. So the cylindrical shell, 2 pi r. That's if you took a cylinder and tore it apart and formed it into a rectangular prism. The 2 pi r would be the length. The width would be the delta r, and that's this guy right here if we're looking for it. That's this other little mini guy. It was green actually. Maybe that'll show up on the video better. That's my delta r. Here's my r, and then the height is going to be the height of the cylinder. So if we're thinking about the shell method, and I know con is what I gave you first, and I gave you my notes. This is length times width times height. It's the volume of a prism. However, where was the prism obtained from? It was taking a cylinder, snipping it down one of the sides, all right, and then it breaks open, and then you unfold it into a rectangular prism. So if you unfold it, imagine reconnecting this piece to that. That's the circumference of the cylinder. Okay, that's this piece right here. So this whole length from there to there is this piece around. So when we cut it down the middle and we pull it apart, we will get that being the length, which is akin to the circumference. We'll have the height, obviously, which is still the height right here. And then we'll have this little piece right there, which is the thickness of the shell. So that's this outlined part right there. That's what we're talking about when we use the shell method. Okay? So let's do this problem. This is kind of a neat one. That's why I picked it. All right. So that's the background on the shell method. Again, you guys should be doing your due diligence and figuring out your Khan Academy stuff. So now all we need to do is figure out what we're going to put in for R's, delta R's, and H's. Okay, well, here's my slice. We're going to go back to it. So if my slice is right here, the radius is a horizontal distance that we don't know. A horizontal distance that we don't know. A good thing to call that is x. Therefore, if I'm going to rotate these pieces around, if r is equal to x, then delta r has to be equal to delta x. Okay, so that's pretty cool. And now we just need to put in some key, nice ordered pairs. Alrighty, so the reason I drew it on here, if this whole, now that was the radius of my slice, but if this is the radius of my right circular cone, then this ordered pair right here is r comma 0. If this is the height of my right circular cone, then that ordered pair is 0 comma h. So what we can do here is we got to go back to the slice. All right, the slice, or the height of my overall cone versus the height of my slice. The height of my slice clearly needs to vary depending on where I draw it. All right, we're trying to draw all these shells, and all these shells have different heights in different radii. So the idea here is we need to come up with the equation of the line, the function, that would represent the height, this random y value right there. Okay, so 2 pi x with r equal to x, the radius of my slice equal to some random x. Delta r, the thickness of my slice, therefore equal to a small change in x. And then as we sum and we use more and more of these cylindrical shells, delta x would obviously go to 0. That's where the limit comes in, the integral, et cetera, et cetera. Retying some basic Calc 1 end of the year concepts. H, the height of the slice, happens to be this height right here, or any one of these heights inside of this triangle. I'll draw that a little bit better so we can actually refer to it easier without me gumming it up. So here we go. So the height of my slice, again, here's the radius of my slice is x. The thickness of my slice is delta x. This height right here is a y value measured from the x-axis to some point on that line. Well, boy, wouldn't it be nice to have the equation of the line? It sure would. Boy, I need a slope and a y-intercept. Oh, wait, we have a y-intercept. It's some height. We have a slope. It's down h, right r. So there's the equation of your line. Your volume, therefore, would be 2 pi x h minus h over r x delta x. Therefore, my total volume is going to be the summation, and I'm going to pull out, well, let's see. I can factor out an h. I can split this up into two separate integrals. It doesn't really matter. I think I'll just factor out the h right here, and I can pull 2 pi h outside of the integral, and then, therefore, I will have x times 1 minus x over r. Okay? So let's see. If I pull the h out, that's a 1, and this is 1 over r times x, so x over r. I have the x. Yeah, we're good. Okay, now where to where? Well, we're going in the x direction, so the domain is we're going from 0 to r. So the constraints on my integral, 0 to r. Ready? And now we're going to do the world's pretty much easiest integral. 2 pi, h is a constant, as is r, because we're talking about the radius of the cone, aka the base of the triangle. And what we're going to do is clean this up a little bit. I'm going to distribute the x. That's what we're getting. Okay. So we just gotta integrate x. Oh, that's easy. 2 pi h. I'm gonna get 1/2 x squared. How do you integrate x to the second? Well, it's going to be 1 over r times 1/3 x cubed. And we need some parentheses here. That's going from 0 to r. All right. So we're just going to evaluate this thing. If I plug in a 0, everything's going to 0 out. So that's cool. So the second part of my fundamental theorem, we don't have to worry about. I'm going to do the first part now and just plug in an r and see what happens. I'm going to get r squared and 1/2 of that. So let's see. Flip this over. 2 pi h x squared minus 1 over r times 1/3 x cubed from 0 to r. That's what we're working with. So here we go. Fundamental theorem. 2 pi h 1/2 r squared minus 1 over r times 1/3 r cubed. It is absolutely killing me, and then minus 0, because if I plug a 0 in, everything zeroes out. It's absolutely killing me that I'm writing that as 1 over r times 1 over 3, but that's okay. All right, let's distribute 2 pi h, and let's see, half of 2 is 1, so I will get pi r squared h for that first part, and right over here I will get 1/3, no, actually, so I'm distributing 2 pi h. So this r cancels out. I have r squared left over, and I'm going to have 2 pi h r squared all over 3. Okay, so let's subtract. Let's see. 3/3 minus 2/3 is 1/3. 1/3 of what? Pi r squared h. Pretty sweet. All right, that is, by the way, the volume of a right circular cone. It is 1/3 the volume of a cylinder. In case you didn't know that, you can Google it. It is right. Okay, so that's how you use the shell method. Again, hopefully that was worth it. Hopefully you'll watch this. And Alexa, play some Slayer.
Here's a station based on Slayer.
Alexa, turn it up loud.